going to do a cool demo. I'm going to have two balls. I'm calling this demo momentum and two balls falling. I'm going to have two balls. The heavier ball is going to be on the bottom, and then the lighter ball is going to be on the top. And I'm going to have them fall from a certain height, right? And then what you're going to see is a very interesting phenomenon that happens. When they fall together, right, they hit the ground, both going at about the same velocity. This one V final, okay, V final. But then what happens is the bottom ball will kind of reflect back slightly earlier than the top ball. So while the bottom ball is reflecting back and going up, the top ball is still kind of coming down. Right? So imagine the bottom ball is kind of reflecting back. I'm going to assume that the collision of the bottom ball with the ground is perfectly elastic. So when it goes up with the same velocity that it was going down and hitting the ground, right? So this is V final, which is the same as this V final, but it's just going up. The top ball, which is lighter, is still going down instantaneously, right? V final. So the bottom ball I'll call little m, the top ball I'll call little m, and the bottom ball I'll call big M and little m, right? So then what happens? The top ball is coming down and the bottom ball is going up with the same velocity. The bottom ball is going to win, right? The bottom ball is going to hit the top ball with a velocity and it's going to send it up. So at the end, it's going to look like this. The top ball is going up with a final velocity. The little ball is going to go up with a final velocity we can call V final prime, which is going to be larger than V final. And so it's going to send the small ball up very, very high heights, right? You can send the small ball up maybe sometimes 10 meters, 15 meters. So you can have a good fun lab you can do with this. So I'll have the camera pointing to the side now. 1 meter. So I have the ball right here, 1 meter. Then I have the other small ball. So this is the blue ball is the small ball, and the big ball is the heavier ball on the bottom. So it goes down, okay? And then you can measure how high the top one went, right? You can see that the top one sprang up really quickly, okay? Okay, so you can see it almost hit the ceiling right there, okay? It depends if you line it correctly, where the small ball is at the center of the big ball, you can have it go farther out. Okay, so it hit the ceiling and it even made a sound. Meters. Okay, about 3 meters. 2.5, 3 meters. So let's do the calculations. Can we actually predict how high the small ball should go up once this happens? And should it be around 3 meters? Let's see if the calculations work. Okay. Of course, the measurements depend on their mutual masses. So for now, let's assume the basketball is 3 times heavier than the little ball, right? Let's see what the calculations will come out. So the basketball, 3 times little m, and then the small ball, little m, right? So first, let's predict what the final velocity is when they're both going down. They're both going to go down at the same final velocity. Assume, of course, that air friction doesn't affect the system too much. So we can say V final should equal square root of 2 times gravity times the height, right? So then we can put the 1 meter for the height. We can say the final velocity is square root of 2 times 9.8. So that's square root of 19.6. So then afterwards, the basketball reflects back at the same speed, right? So this is a 3m. Reflects back 4.43 meters per second, while the small ball is coming down at 4.43 meters per second. So now, for a second, let's treat this just as a pure momentum problem. Assume when they collide with each other that they collide perfectly elastically at 4.43. So I'm treating it purely as a horizontal problem. And then small ball here, m, going at 4.43 meters per second that way, right? So then the initial momentum of the system is going to be 3m times 4.43 minus m times 4.43, right? So then it's just going to be, the initial momentum is going to be 2m 4.43, right? Now after the collision, what's going to happen? This 3m is going to be going this same direction, but slowly. In other words, the 3m, the basketball is going to still be going up, but slower than it was, slower than its 4.43, right? So the 3m is going to keep moving the same direction, v1, while the m is going to be shifting directions, right? It's going to be moving this way at v2. Right? So the final momentum is going to be what? 3mv1 plus mv2. So let's put that here. P final 3mv1 plus mv2. And then we can set that equal to 2m 4.43, right? 3mv1 plus mv2, and then the m's cancel, right? So then we just have 8.86 m is equal to 3v1 plus v2, right? Now we're going to impose kinetic energy conservation. The initial kinetic energy of the system right before the collision is equal to the final kinetic energy of the system right after the collision, okay? So what will that equal? So the initial kinetic energy is equal to 1/2 3m 4.43 squared plus 1/2 m 4.43 squared, right? Okay, so then of course this is just going to be 1/2 3m plus 1/2 m, so everything else is the same, so it's going to be 1/2 4m. 1/2 4m 4.43 squared, which is just going to equal what? 2m 4.43 squared. Okay, now let's calculate the final kinetic energy of the system. Right? Kinetic energy final. Okay, so then I have 1/2 3m v1 squared plus 1/2 m v2 squared. Okay, and then I'm going to set that equal to 2m 4.43 squared, because I'm assuming perfect kinetic energy conservation, right? So that's equal to 2m 4.43 squared. Okay? So then I'm going to erase these so that I could do my calculations. Okay? So then the m's cancel. Okay, so then I have here 3 halves v1 squared plus half v2 squared is equal to 2 times 4.43 squared. Okay? And you could just simplify it by multiplying everything by 2. 3v1 squared plus v2 squared is equal to 4 times 4.43 squared. Now I could do substitution. I can say, okay, from here I can see that v2 is equal to 8.86 m minus 3v1. In reality, this m should have disappeared, right? Because I got rid of that m, and then I should have gotten rid of this m also. Okay? So then it should just be 3v1 plus v2 is equal to 8.86, right? So then I can say v2 is equal to 8.86 minus 3v1, right? And then I can substitute that there. 3v1 squared plus 8.86 minus 3v1 squared is equal to 4 times 4.43 squared. Then I can expand that out, 3v1 squared plus, and then when you square this, you're going to get 9v1 squared minus double the product. So when you do double the product, it's 6 times 8.86 v1 plus 8.86 squared. 8.86 squared. Okay, so then let's put all of this together. V1 is equal to 0 and V1 is equal to 4.43 meters per second. Okay, so then what does that mean? Well, V1 was the velocity of the basketball, so that means the basketball was 3m, and then this little m was coming this way, 4.43. So V1 was the speed of the basketball after the small ball hit it. So this is V1, and then V2 is the speed of the small ball, right? So one of the answers that is saying V1 can either stop or it could be going 4.43. Well, this is how I know that my calculations were right. One of the answers I got, 4.43, is the same as its initial speed. That means nothing has changed. If this has the same speed as that, and then that still has the same speed as that, that means the collision never took place and you've conserved kinetic energy and momentum. So usually in elastic collision problems, one of your answers, which was this one, is going to be the same as the original speed of the object. So the other answer is the one that we're looking for. So it's saying that what should happen to the basketball is that it should stop, because this one is imparting enough momentum to it to completely cancel it, right? So then this one should completely stop the basketball, right? And then the small ball should go back. At what speed? Well, what was the equation? Is equal to 0, then V2 should be 8.86 meters per second. So that means the small ball should not only reverse itself, but it should double its speed. It was going originally 4.43, the final speed should be 8.86. Okay, now with that, how high is it going to be able to go up? When it goes up to the top, it's going to be 0. The velocity that the small ball has when it's going up is this one, 8.86. So we can say H final is V initial squared over 2 gravity. So V initial is going to be 8.86. Well, 4 meters, that would have gone, not only hit the ceiling, but it would have gone even more, right? So it's predicting that it's going to go up 4 times. Well, that kind of makes sense. If the velocity doubles, right? If the velocity doubles, then you square that, that's going to be 4. So the final height is going to be 4 times the original height, right? If the velocity doubles. If I run this several times from 1 meter, you see, if you look at the basketball, if the small ball was not on top of it, it would have completely bounced back. You see? It would have completely bounced back. But the small ball is preventing the big ball from bouncing up. And you can see, as soon as it goes up and the small ball hits it, then it goes back down again. It kind of stops. So, and then the small ball goes up all the way and hits the ceiling. If we were doing this as a more detailed experiment, we would actually measure the mass of the ball, the 2 balls, and then run this several times, measure the maximum height it goes up to, and then we could compare the two and calculate a % error, okay? Thank you very much.